So this is Applied Quantum Mechanics, PHYS 3022. So welcome to this Applied Quantum Mechanics course. I believe many of you, a majority of you, have just finished Professor Liu's Quantum Mechanics 1. And I believe that he has prepared you well for this course, better than what I did in previous years. I looked at the notes and they were brilliant. So in this course, it's quite different from the other major courses that you have taken or you are taking. In the following sense, in the other major courses, usually you will focus on one particular theory and then you crank on the formalism. In this particular course, instead, I emphasize the fact that most of the problems in interesting physics, problems are not exactly solvable. Thereby, the first thing I want to do in the course is to develop some approximation skills. If you move on to learn more physics, more often than not, you will find that doing physics problems require good sense on making appropriate approximations. And you will see a lot of approximations in this course. Another aspect that this course is different from many other courses in the curriculum is that it is basically a course about the physics of matter. By that, I mean the physics of atoms, molecules, and you can extend it to understand the bigger thing, solids, or even the smaller thing, the nuclei. You will see that there is a coherent physical picture that emerge when you study these different areas of physics. They just look different. Nonetheless, there is some underlying principle behind this seemingly different subjects. So I would say it is a rather interesting course. I have been teaching it for a few years since the new curriculums, the change into the 4-year curriculum began. So let me start. Just to lay out some guidelines. So you are here, so you know the course that you are taking, okay? And then I will post the class notes in this particular course web page inside the departmental page. That is more convenient for me instead of every time go into the Blackboard, open a folder and so on, okay? And I believe it is also more convenient to you because in the meantime, I'm not setting any download passwords. So we will have meetings Tuesdays, Thursdays. So this is our first meeting. And we will have 3 exercise classes in a week. You should attend one class. This exercise class is an integrated part of the whole course in which the TA will work out some sample questions for you. So they are like worked examples to the formalism or to the idea that we discuss in class. It is a very important part of the course. I have sent you the Zoom link and therefore you are here, okay? So in one document, you have the links to classes, you have the link to the exercise classes, and also each TA will run a 2 hours of consultation per week, so that you can grab them and ask them questions. I also give you a timetable that you can easily find out which time slots are the TA's consultation hour yesterday, right? Okay, so are the TAs around? I saw some name, Mr. Young is here. Okay, so let me go on with the assessment first. The problem sets will be accounting for 30%. There will be a midterm, there will be a final, 25 and 45% respectively. The exact format will be announced later, due to this uncertainty in the pandemic situation. And all the students must note this is a major theory course, thereby among this 25 plus 45, 70% that is, in the written exam part, a student should at least obtain 20% to be considered for a passing grade. It is a necessary but not sufficient condition. I will give you problem sets along the way, maybe 6 or 7 of them during the term. And then, of course, independent work is expected. Although you are encouraged to discuss with your classmates. You are in year 3 or some year 4 students, I recognize. You know that CUHK has a zero tolerance policy against plagiarism. That means don't copy homework. And if you are still not sure about the policy of the university, click this link and read the details. There are guidelines, and also there are penalty guidelines if you violate some of these guidelines. This term, I will set up some submission folder inside Blackboard so that you can submit your homework online, so that the TA can also conveniently mark your homework without printing things out. Like other courses that I taught, I will have a T+2 policy for homework submission. There will be a deadline. If you submit it by the deadline, that's fine. If you are too busy, in some weeks, there are many tests, lab report, etc., and then you couldn't meet the deadline, don't worry, you have 2 full days buffer. You can still submit it within that buffer time of 2 days, although there will be a 20% discount in the score of that assignment. It is to encourage you to try, okay? And also the sample questions every week are designed to illustrate the idea, as well as they are designed to be rather similar to some of the problem set problems, so that if you attend the exercise class, you should be able to work out a big part of a problem set. The TAs are Mr. Yang Cheng-hei and Mr. I forgot the Chinese name, Zhou Jianren, okay, and Mr. Eric Kwok, okay. I wonder if the TAs are here. Mr. Young, are you here? You are here,
yes,
right?
Yes, I'm here.
Okay, could you let the students recognize your faces?
Okay. Let me.
Okay, so now this is one of a brilliant TA, okay? He is also new to this course. The other 2 TAs are veterans. They have done this before. Okay, how about anything you want to say to the students, give them some advice? You have gone through this course, right?
Yes, I think, yeah, I think Professor Hui is a very good professor. So yeah.
That's it.
Yes,
Oh,
yeah. So be excited to learn this course under Professor Hui.
okay. I think we expect you to work hard to help the student learn. Okay. How about Eric? Are you around? The list is so long that I cannot look at it. Okay. And Zhou Jinren, no. Okay. Both of the other two TAs have done this course before, so they are experienced. And then you may need some essential mathematical skills in this course besides the basic quantum mechanics knowledge that you acquired in the first term. In case you need some, click this link. There is a site in the department, in the physics department with a module of useful mathematics techniques. And also, if you go to the front page of the course page, you will find a link to all the reserved books in the library under this course. Or you go to the library reserved book, look for PHYS 3022 on the computer search. Then there's a list of books that I reserved under this course. They are put in the glassy room. The room, you go in the library, turn right. There is a room with glass partition, inside which you can find all the useful books relevant to this course, including a few very useful mathematics skills textbooks. Okay, so that is a basic layout. And then, so yesterday I have sent you this thing. Okay, so keep this with you. I also send you as a separate file so that you can easily go to exercise class, ask TA questions, and come to the lessons. Okay, I have also posted inside Blackboard this file so that in case you have lost the file somewhere in your computer, you can log into Blackboard and then get this one. Okay, so there's no reason to miss the class. So let's get started now. So let me give you an overview of what we are going to do. Although you cannot drop this course, it's a major required course. Okay, nonetheless, it's good to know what will be done. So the logic is as follows. You have learned a lot of quantum mechanics concepts and also the abstract thing, operators, measurement, manipulating spins, and also some very concrete problems. For example, particle in a box, harmonic oscillator, and also rotor. I think Professor Liu did the rotation problem, the rotor problem, and then also the hydrogen atoms. Okay, so for these problems that I mentioned, have you done that? Can someone just type in, tell me? You have done that in the previous term, right? Is that right? Hello, hello? Okay, wonderful. Okay, that's what I need for this course to kick off this course, basically. Okay, and you realize these 4 problems that I mentioned, of course, they are more, okay? Infinite box, harmonic oscillator, rotor, and hydrogen atom, they are exactly solvable. Okay, in 廣東話 is 有精確解嘅 ，OK， 普通話精確解的。And you will find that they are good starting points for understanding a big family of physics problems. For example, the harmonic oscillator basically is the most important problem in all of physics. The more you learn, the more physics falls into the scope of harmonic oscillator. More down to earth, how molecule vibrates, how solid lattice vibrates, and more abstract go on. Oscillator is basically the way to understanding why we have particles. That is part of quantum field theory. So the oscillator problem is really important. The hydrogen atom problem is also important in the following sense. It is probably the only atomic problem that you can solve exactly. So it's rather sad. The whole periodic table is rather big. I think the elements now go to something like 118. You can go onto the web, look for the latest version of the periodic table. I think the elements now go to 118, 119, something like that. We can only solve the Schrödinger equation for the first element, the hydrogen atom. Very soon you will see that even that is not 100% true statement. The hydrogen atom problem that you solve exactly, the Hamiltonian is an approximation. There are missing terms. There are missing effects. To mention a little bit, for example, there is something called spin-orbit interaction, where the orbital angular momentum of the electron will interact with its own spin. Electron is spin half. Thereby, there will be an additional term in the hydrogen atom Hamiltonian. With that term, that will make the hydrogen atom problem more difficult to handle. And we will do that in this course, using some skillful technique in approximations. So that is why the first point here, you have acquired basic concepts and skills in the previous course. And here we will apply those concepts and develop some additional tools in your toolbox, in particular, how to think in approximation and how to do approximations in order to understand a wide range of physical problems. What are they? We will do atoms, we will do molecules, we will do how light affect atoms and molecules. That is light interacting with matter. That is a big, big problem. If you just take your atoms, don't do anything to it, you don't know what's happening. You ought to prop the atom. In doing so, a convenient way is to incident light into it, and then you have atomic spectrum. And that is how the whole quantum physics was initiated. In 1885 or so, around that time, we have this hydrogen spectrum with Balmer series, Lyman series, things like that. Why do we have those lines? That has to do with light matter interaction. And we can move on to use the same tools to understand some solid states or nuclear physics. That is, in the middle, we have atoms, molecules, they are in the angstrom scale. We can move up to bigger ones, solids, or we can move down to smaller ones, the nuclei, okay? Particle physics is another related problem, but the Schrödinger type of quantum mechanics is insufficient to handle those particle physics. We need relativistic quantum physics. So this is the plan, this is the scope. So here's a big picture, don't worry, I will not read them out for you here. Along the way, you will pick all these things up, okay? So you see these arrows. The most important part is this box at the beginning of the course. We will develop some approximation methods, namely perturbation theory, 微繞圍繞, and also variation method, 變分法, and then I will introduce the big picture, the physical picture behind how we could avoid doing many particle problems and instead doing single particle problems, and we can still understand much of atomic and molecular physics. Think about it, the atom problem. I give you a uranium atom, 92 electrons. There are 92 times 91 divided by 2 pairs of electrons, right? So Coulomb interaction will kill you, right? You can, well, of course we know the Hamiltonian, okay? But if you think about it, well, how could you solve the 92 electron atomic problem? It's hard. Nonetheless, we can still acquire a rather good understanding of such an atom. We could rather successfully, though approximately, avoid handling the electron-electron interaction, okay? What is the idea behind it? We will discuss it. The very fact that we exist, we are here to talk about physics, is that there are molecules. We are formed by atoms, molecules, right? A lot of water in our body. So, as a physics student, we better have a good sense about how atoms could possibly come together to bind into a molecule. Solid, you can still think about it as a big molecule. It's true, right? So 10 to the 22 atoms come together to form a piece of thing. You call it solid. I call it a big molecule. That's fine, okay? Therefore, if you understand bonding molecules, it is the starting point to understand solid state, and also a big part now called material science. We will do that. It is a wonderful place to appreciate the power of quantum mechanics. We could not necessarily use many equations, but we could have a good way of realizing how the atomic wave functions come together and then they form bonds, okay? So that is a big part of our course. With this idea, then we can go to atomic physics and understand spectrum, the periodic table, how to handle atoms beyond hydrogen. And then we can go into molecules to understand what is covalent bond, what is ionic bond, things like that. At the end, you will find that we don't need those names. It is just solving one Schrödinger equation problem, okay? And then in nuclear physics or solid state physics, there are also a big class of problems, solid state, for example. Why do we have conductor insulator? Okay, again, under one umbrella, solve the Schrödinger equation, put the electrons in, the end result will tell you whether it is a conductor or an insulator, all right? So, and you see, we have a lot of topics to cover, thereby this course runs in a modular manner. So you will see a part there about approximation. After that, we will make use of this approximation to understand atoms. After that, we put in light to interact with the atoms. We have some light matter interaction, and then we have a module on molecular physics. If time permits, we will have some nuclear or solid state physics, okay? So each module will be something like 3 weeks, 4 weeks at most, okay? And my goal here is this. I would like to train you a bit about using those quantum mechanics 1 concepts and develop some sense, physical sense. So I will emphasize some big picture instead of many equations. If there's a choice, I will convey the big picture first and then fill in, back up my picture with some quantum mechanics manipulation, okay? So again, I also would like to balance quantum mechanics and quantum physics. In quantum mechanics, the emphasis is more on formalism. Hermitian operator, there are real eigens values, things like that, okay? But in quantum physics, the emphasis is on the physics part, the phenomena part. Why atoms have discrete energy states, and why do you have spectrum? Why some spectral lines are brighter, why some is dimmer, why some line is are missing, okay? So those are the physics part. Here we will try to balance these two parts of quantum world. So I have mentioned that I reserved many books. I encourage you to check the list out, okay, and then see what books are there. So my goal, tried at least, is to convey to you that basic quantum mechanics can really do a lot of things. You don't need to keep on going deep into formalism, okay? Many students like formula, okay? At the end, you lost the sense. I would also like to convey the art of thinking like a physicist. Very often, you don't need to write down so many equations and solve them. If you understand a few basic concepts, you could make use of them to think into more complicated systems. And then I would also like to convey the physical picture of some physical phenomena and the theories behind it. For example, bonding, okay? And then with this picture already conveyed, I will paint the picture by equations. I hope that I could succeed to some extent, okay? You are year 3, 21 years old, I guess. So the whole world, you know, in front of you is many opportunities. So I would also like you to be aware of what are happening in the frontiers of physics. Nowadays, with online web, things like that, it is much easier for your generation to get to know what is happening at the frontiers than when I was an university undergraduate student in Hong Kong at that time. I have to wait 2 months for the Physics Today magazine to arrive in the library. Now, you can easily register free of charge with the magazine, and they will send you every day or a week, every week, what is hot in physics. So your generation is rather, I would say, have the luxury that information is rather easy to get. So then I think there's no excuse for you not to be aware of what is happening at the frontiers of, for example, particle physics, nuclear physics, atomic physics, things like that. Okay, so as we proceed, if there's something new come on, maybe I will mention it a little bit. Okay, and then at the end, I hope that you have an appreciation of the effectiveness of quantum mechanics. A simple Schrödinger type of thinking could really do a lot of things, okay? And the revolution that it is bringing, okay? It has brought already, that is the first quantum revolution. And what is happening now is often called the second revolution, the second quantum revolution. You must have learned a lot from Professor Liu's course, and that will equip you to meet the second quantum revolution meaningfully. Okay, the second quantum revolution emphasis on superposition and entanglement, and I think you already have some encounter in your previous course on that. And one point is that many students always say that they are rusty in mathematics, therefore they could not appreciate the wonderful thing about quantum mechanics. I don't think that should be the case. So quantum mechanics is much more than just mathematical manipulations. And then, so I would try to convey that physical sense on one hand and mathematical manipulations on the other hand, actually, they help each other. They complement each other, okay? And as the course proceeds, I hope that you will get this sense, you feel this important point more and more, okay? So we will start the course with some approximation methods, because I would say most quantum mechanics problems are not exactly solvable. As I said, as simple as helium atom, okay? 2 electrons. There's no exact solution, rather sad. But the happy thing is that no, we can still understand a lot of them, okay? A lot of the physics of helium and other atoms, okay? So we will try to see how this thing goes. A word and advice, how to do well in this course, okay? My experience is the following. You should have an open mind in learning. Be brave in making approximations, okay? Now, that is my experience over 30 years of teaching, I would say. Many students, especially CUHK students, their approach to physics is more like equal sign by equal sign by equal sign, okay? Exact. But then when they get stuck, exact, what is the next equal sign that is exact? If they get stuck, they really get stuck, usually, okay? Many lack the drive to find the way out. 揾路轉啊, okay? You can't do that You've tried to find a way out, okay? And that way out usually means making some meaningful approximations. Students should try, especially in project work, in research, whatever way to get an answer. Even on the way, you have made some approximations. Often, the answer will tell you whether you have done something right or wrong, of course, okay? But at least you take the problem to completion, and then the answer will tell you something. But if you just get stuck in the middle, you're not getting anywhere, okay? So that's what I meant by keep an open mind in learning, okay? Another point is that you should be willing to take a physical picture in and then move on, instead of seeing every equations line by line, okay? Sometimes deriving something out is so different, maybe some missing point is out of your scope, but if you get the result and then move on with that result and use that result to understand a lot of physics, the return is much more than you try to crank on how to get at that particular line, okay? That's what I meant by, you are willing to take a physical picture and move on. And then the second point is be open-minded in handling equations and mathematics. Mathematics is needed, of course, to turn the physical picture into some formula, okay? More important, I would say, is to understand the meaning and the implication of a particular formula. So you have a formula, there are several terms. What are they, okay? So that is an important part. And then if you know the meaning, you put them together, you have the formula, okay? So if you know the meaning of these terms, again, that understanding is more valuable than you know how to derive it, okay? So we will do some derivatives, we will do some integrals, and we need to do some matrix manipulations. But as you will see, if you know how to do 2 by 2, you know a lot of physics. Okay, I'm not kidding. Okay, so the assumption that you know how to do 2 by 2 matrix is very humble, right? If you claim you know a little bit of matrix, 2 by 2 is the smallest size. All right. So, but really train yourself to know how to manipulate 2 by 2 matrix. You will know a lot of physics from the manipulation. So the practice to do well is to read the examples, the sample questions, read the questions in the problem sets carefully. Sometimes I want to teach you something through the problem set questions. And then try out the problem sets by yourself, okay? Cleanup questions, the TAs run the 6 hours of consultation hours per week. So there's no reason why you say they're time fresh, things like that, okay? Clean up the questions that you have. And then train yourself to do some jump in on time reading, okay? It is an important skills. Again, generations of CUHK students don't have that trained well. What I mean is that take a book, you don't read from page 1. You only need, for example, time-independent perturbation theory up to 2nd order, okay? You want to read something about it. You should train yourself that you can jump into that and then maybe start with, 2 pages before that set up the problem, and then you start to read it, okay? So many students have the habit that pick up a book, start from page 1, and stop at page 40. then you never get to the point you want to learn, okay? That is not a good thing, okay, as time goes on in your career. So background assumed, okay, I already mentioned that. So I already mentioned a few problems that you have solved exactly in the first term. So here I checked that with Professor Liu's notes. They're all in, okay? So Hermitian operators, and then angular momentum, spins, some exactly solvable problem, boxes, finite well, oscillator, everything you have done, I believe, okay? So these are the assumption, and I will use that. So just to be very explicit, there are this kind of problems, particle in a box, you have done that, oscillator, you have done that, central force problem, or in quantum mechanics usually called spherically symmetrical potential problems. And then a particular case is the hydrogen problem. This is the Coulomb potential energy function, okay? So you have solved this. If you know, at least you have something in mind about these problems, you are ready for this course, okay? So I think at this point, maybe I will take a break and then we will start chapter 1 of the course, okay? So let's take a break for 10 minutes. We will resume 10:25, how about that, okay? So I will stop sharing and then I will be around. If you have questions, you are welcome to ask.